Today we're going to talk about the CPT for advanced functions. You have the choice of two different options, and I've tried to make them about the same amount of work, but of course one may appear easier or more straightforward to you, and maybe that's the one you could consider depending on how it's going in your other courses and everything. Let's talk in brief about what each of the two options are. And then following that, I'm going to do a deeper investigation into what am I looking for? I'll go through what you need to do for each one in a sort of more detailed way. So this first sheet here is the function. If you can just find it here, I'll just show, just so you can find these things too. Just down at the bottom under CPT. Okay, so there's MFH4UQ CPT, and then there are the two submission templates. Depending on which one you choose, you would load that template and fill it out. So option number one is to do some function art. I took this one. You can see this one is just call it up here. It's from one of my students from last semester, and you can see. He just did an amazing job here, right? With how many functions does he have? I mean, he probably has 30 of them. I mean, I'm not asking you to do 30, although, again, this guy got 100%, so maybe that's some inspiration. People got 100% with less than this, but you can see the functions that he drew, right? Variety of different functions. He's got some polynomials. He's got some rationals. He's got some roots, some exponentials, and even some combinations of functions. And that's kind of what what I'm just going to break down for you here and what's required. So what I'm asking for in this one is that you find an image that you think uses different patterns of functions that we've learned about. You draw your image using at least two functions from row A, two functions from row B, and one from row C. So of course you can have more than this, and if you I don't know, some people, when I did this last year, they just really got into it and they drew amazing things like this one, right? Like the one I was just showing you, and again, I'm trying to make it so that if you want to, push it and excel and really show me what you can do, this project gives you the option. But if you're, strapped for time and you're really, struggling and I know there's a lot going on and so on, I want to make it very doable, and you'll still do, reasonably well, right? I mean, I can't promise 100%, right? But of course, if you do what I've asked here, you're definitely, in the 80s, let's say, and the more you can kind of push into more complexity and better matching and all that stuff, the better you'll do. So you pick two functions from A, two functions from B, and one from C. So for A, it's looking like, rationals, reciprocals, linear or polynomial. And just wanted to call this up for a sec. Yeah. Okay. So those ones that we learned. Basically, the A is like ones you might have had a bit of familiarity with before advanced functions, right? And then B is more like the more complex ones. I mean, I know we would have touched on these in grade 11 too, but there's kind of like the difference there and there. And maybe let's now that I'm thinking about this, let's switch this one with this one, because those are probably makes more sense. Okay, and anyway, so, and then row C is where you do a combined function. I'm only asking you to do one because these ones are, more involved, right? As you've been learning in Unit 4, when you combine functions together, there's a whole bunch of unpredictable and sort of more complex behavior that emerges. So we're just going to take one from there, although again, you feel free to use more. Again, I think using a composite particularly is a really strong way to show your knowledge, but really all of these are pretty effective if you can manage to use them. Okay, so you use various GeoGebra commands, dilate, rotate, translate, to help fit your function. Okay, so I'll show you how those ones work in a little bit more later on, but just as a simple example, let's imagine I wanted to do, like a wavy kind of pattern, but I didn't need it to be straight, right? So let's say I type function sine x, and let's maybe make it a bit compressed. And let's say I want it between 0 and 5. Okay, so I've got that little bit of waviness. And let's just make it a little bit bigger, sorry, between 0 and 10. 0 and 10. Okay, now just for sake of argument, I'm just going to show quickly a couple of commands on GeoGebra you can do. So rotate is one of them, right? So I can rotate the function f, and let's say I want to rotate it, pi over 6. And you can see that now what I've done is I've sort of taken the sine wave and sort of twisted it a little bit, because maybe that's going to fit my image a little better than otherwise. I can also take my function and dilate it. So dilate just means like expand. So I could dilate f1, which is my new function, and I want to make it like twice as big. So it's too small right now. I want to make it bigger, right? So I can dilate it to make it bigger. Finally, let's say this isn't exactly where I want it to be. I can translate it. Okay, translate, and then what it says is object and vector. So quickly, a vector is just like a point where you want to send it. So let's say I want to move this thing 3 points left and 5 points up. I'm going to make a vector, -3, 5, right? And basically a vector in GeoGebra is made by using a lowercase letter and then a coordinate. So like 4, 4 would point that way. Now what I'm going to do is I'm going to go translate. I'm going to translate my function, which is a, and I want to translate it according to vector v. And now you can see that it starts over here instead of starting down here. So these three commands, dilate, rotate, translate, will really help just make, you can always sort of start your function at the origin, and then you can kind of move it where you need it to fit your picture. You do not need to complete the picture. Okay, so even in this one, which was amazing, he doesn't have a complete, every single detail in the picture is here, right? I mean, a lot of it is, but not all of it, right? I mean, like the eyes, for example, and the different ears, and like there's lots of stuff that is not necessary. I can see that this person's command of functions and making art with them is very, very strong. I don't necessarily need every single line, every single detail of the image covered, even for 100%, right? I mean, even someone who got perfect didn't need to go to that degree. Okay, so how it will be marked, you will have to come up with the domain, range, and other features. And when I say other features, I mean what's over here, right? Maxes, mins, increasing, decreasing, positive, negative, end behavior, that sort of stuff. As I mentioned, asymptotes. And you catalog those things. For application, you have to pick. You have to give me 4 functions that accurately represent the picture. So again, if you're like, give me 4 functions, but they're not a particularly good match to your picture, like they kind of miss it by a while, and again, it's not going to be perfect, but I am expecting it to be pretty close, right? And again, this one I think is a good model to show, where it's just like, again, it's not like perfect. You could zoom in, you could find little areas that don't match perfectly, but overall, this is very, very strong, right? I can see a lot of attention to detail was placed, especially around like this head, right? Like all the different functions that were used, to model that. So again, I'm looking for like the accuracy of it, the quality of it, the quality and detail, and then the complexity of your functions chosen. So once again, I've tried to sort of force you to pick a variety of functions here, right? So I think as long as you sort of follow my template, everyone should do reasonably well there, right? So again, let's choose a variety of functions, make them reasonably complicated, move them, dilate them, and so on as necessary. For communication, I've asked you to write me a short paragraph explaining how you made the picture. I'll go into a little more detail about that. And then you have to do a rate of change calculation. So rate of change, I believe we just started it in Unit 4. There's one more lesson on it towards the end of Unit 4. Now for thinking, it's a function analysis and a quality and detail of the match, but specifically for your row C function. Because your row C function has, it's more complicated, right? And how you made it and stuff. I'm more interested in that. Okay, so that's the whole task, right? And what I'm going to do at this point is just, I think I'm actually going to undo that change from before. I'll just leave it the way I had it before. It doesn't make a big difference. What I'm going to do now is let me talk through the other model, and then I'll go into detail about each one. So it's kind of like, well, yeah, you can watch as much of the video as you want, of course, but if you know for sure which one you're going to do, you could like skip to that section, right? Now, the second option is to do data modeling, where what you're going to do is you're going to find a data series that's interesting to you. So the one I'm going to demonstrate for you in the longer part is the U.S. national debt. I'm going to basically, this model right here, you can see all the dots that were created are my data, and I've created this brown function that's sort of underneath it that I think is kind of modeling that data and showing a function that sort of maps onto it and maybe can make us predictions. I've asked you to use two different models to do this, so maybe in my example I'm going to use a exponential, and then like when I'm looking at this, it kind of looks like it could also be like a quartic, right? Like it's really flat and then it opens up kind of like a parabola. So maybe I'll try a quartic as a second example. I need you to explain the quality and source of the data. So where did you get it from? How do you know it's reliable? That sort of stuff. I want you to compare and contrast the accuracy and appropriateness of your two models. So, my quadratic model, is good during this interval, but my exponential model is better during this interval. Overall, I think my better model is, which one? I want you to use whichever one you think is your better model to make some predictions about the data outside the series. So, for me, what does my model say the debt's going to be in 3 years, 5 years, 50 years, and so on, right? And then I'm going to ask you to discuss whether you think those predictions are, valuable or valid. Finally, you're going to discuss the model's limitations and ways that you could improve it. So, for example, if you had a more advanced function type, like maybe in my model you can see it underestimates it for a while and then it underestimates it. So maybe in my model I need to raise it up a little bit to sort of improve it. Maybe if I could account for this sort of waviness, maybe there's there's a combined function I could use that has a bit of a sine wave to it that maybe would improve it and stuff like that. It's kind of like brainstorming without actually having to do it necessarily. It's just brainstorming ways that the model could be better. So again, for knowledge, I'm going to ask that you analyze the two models, so the domain, the range, any other important features they have, and then you have to make some predictions outside the series. For application, it's basically the whole grade is coming from the data that you've got and the models that you made. So, did you make two different models, and are they very good fits of the data? Do they represent the information effectively? For communication, you've got to choose. I got to see a defense of the source that you picked, and also a link to the source, so I can recreate your work. Right, I can look at the data and reproduce it. And then I want you to write an intro and a conclusion. An intro, I'll talk about this in more detail, but like 2 paragraphs, let's say, where you are talking about why you chose this, why you think it matters, why the model is significant, and then in a conclusion, what did this teach you about the topic you're studying? For me, I could talk a little bit about the debt when we get there, but if the debt is modeled by an exponential function, what does that tell you about the future, right? What kind of conclusions do you think we can draw about this situation going into the future, right? That's where you're sort of doing the thinking, where you're connecting the real world that you're looking at to the model. Finally, for thinking, again, it's a bunch of short answer questions. You're going to discuss your limitations, you're going to compare the effectiveness, and you're going to use some mathematical reasoning to back up what it is you're saying. Okay? So that gives you an overview of the CPT. In either situation, you're sort of you're creating functions and matching them to things and then discussing it. And whichever one you pick, I've tried to make them about the same in terms of their work and detail and so on. But of course, you may feel that one is easier or more suited to you than the other, and you can do that. Let me go into more detail now about how the first option would work. Okay, so this file is called submission template for MFH4UQ function art. Okay, so once again, this is, you can find it down here. It just says submission template, right? So under CPT, you go to here. So each page represents one category, and the first page is your application. So scored out of 15. Here is, I want a screenshot of your picture with the functions. So for example, for me, if I were this student, for instance, I would go and I would take this one, and I would make a screenshot with the images in there, or with the image in there, sort of shrink it down so that it fits, and then go back and take another screenshot with the functions like removed, right? So I can see that in more detail. If you're going to use, some people use Desmos for this, and that's fine. If you're going to use GeoGebra for this, I would also really appreciate in the Dropbox if you could drop off the GeoGebra file itself. Right? It's a little easier for me to work with the GeoGebra file as opposed to the screenshot, but in any case, I'll make a note of that in the Dropbox. So I put my picture here and here. I take two functions from row A. I write them out. What's my function? Okay, so f of x equals 3x squared minus 2x plus 1. What does this represent on the picture? This was the left eyebrow, of the face, or whatever, right? You just give me a very quick description of what the function was. Now, I would appreciate if you could name them different from one another, so that I'm not trying to turn it which one's F, which one's F2, which one's F. Give them a different name, or even if you just give them a name like left eye, right, or left eyebrow, or something like that, or you give them a name that's pretty obvious. I know where to look and how to find them. So then you do your two functions from row B, okay, and that's basically that. It's your application page done. Most of the marks, of course, are going to come from your drawing. And how close your drawing matches, and whether you've listed the functions correctly and all that stuff. Now we go on to the knowledge page. The knowledge page, you can see that you've got two functions from row A, two functions from row B. You got to give me their domain and range. You got to give me their end behavior, and then in the so remember, end behavior is like x approaches infinity. I think that's how you type infinity. X approaches infinity. F of x approaches, let's say we had an asymptote, approaches 3, or something like this, right? And then you go x approaches negative infinity and all that stuff, right? So you write out the end behavior. Now, for special features, each function is different. So, maybe your function only has one, or maybe it doesn't really have any. You can put x-intercepts as well. You can put anything that you think is relevant about this function. So, does it have a vertex? Does it have a turning point, a min and a max? Is there an asymptote? If you can't find any of those things, list its x-intercepts, its positive and negative regions, or its increasing and decreasing intervals. I'm not necessarily expecting you to do all of these for every one. 2 for each one is great, and some functions might be simple enough that they really only have one thing to say, and that's fine, right? So try and do as much detail as you can, but if your function is like x cubed, let's say, for example, then what can you really say about x cubed? It is increasing for x in the real numbers. So I think for real numbers you write double R. Right, x is increasing in the real numbers. You write an x-intercept at x equals 0, and you write negative. So let's say f of x is less than 0 when x is less than 0. F of x is greater than 0 when x is greater than 0, right? That's basically all I can say about x cubed. It's basically everything there is to know about it, right? I can't really talk about mins and maxes because it doesn't have any. I don't talk about asymptotes because it doesn't have any. I talk about what I can talk about, right? And then you just give a description of the function using the tools and techniques that we know. So that's knowledge out of 15 for these 4. Again, I don't want to say, well, it shouldn't be that difficult to score extremely highly in this region, right? I mean, you're just doing an analysis of the functions you created. Now, for when you get to communication, okay, this will be based on your row C functions. You can see at the top, it just gives you the list. What is the function and what does it represent on the picture? So same as before. Now, in a paragraph, and I think this is about the right length. I mean, whatever. It can be a little shorter, a little longer, but I don't think it should be much shorter, right? How did I create the function? So how did you get the idea for it? What were the challenges as you were trying to make it? How could it have been improved with time and more detail? So let me give you an example from the one that I think this student did extremely well, okay, which is this function right here in the gray, which is function t. Okay, so function t, let's just go back. Where is function t? Sorry, right here. Now function t is incredible because it is an asymptote, and then it is a wave, and it is a wave that like has a slope, right? Like it's a wave that's going lower over time. And look at what the student did to create it. He created a sine graph and subtracted a log from it, right? So it's a combined function where there's a log and a sine combined. In this one, right, the one right beside it, which is function s, let me just find function s, sorry. Where is, sorry, just a little small. Oh, sorry, it's right at the top, right? Again, it's a sine plus a log. And what does a sine plus a log look like? Well, if you do sine x plus log, let's just make it log 2, right? What does it do? Well, it creates kind of like a log function. Like here's what the log part looks like. Except instead of just rising steadily like log does, it kind of goes in a wavy pattern, and you can see that like combining the two functions together was something this student was able to do really effectively, right? To to create this part of his model. And so I know this is difficult to do, and it takes time, and it's complicated. So I want to hear about it. Like, how'd you get the idea to do it? What was your first try? Well, maybe give me some tries that failed. How did you kind of get it to fit perfectly? Did you change the period? Did you move it around? So I want to hear about like the creative process for how you made that function. Down here, you make two rate of change calculations. Okay, so find an interval with a positive or negative rate of change and measure the average rate of change on the interval. So, for example, right here on my combined function, like let's say I'm using this one for t, I know that an average rate of change is a negative. It's a line with a negative slope, right? So let's say from d to h, if I make a line that joins d to h, I get an average rate of change there that's negative. So all I'm going to do in my answer is I'm going to say on the interval, let's do an equation. X is in, negative 2 to 4. F of x, or let's say eyebrow x has a negative rate of change. And then I'm going to do my calculation down here, right? So eyebrow of 4, take away eyebrow of negative 2, and then negative 2, sorry. And then I'm going to put it over 4 minus negative 2, right? That's what the average. That's what the rate of change calculation looks like. I'm sorry, I should make it all in one big fraction, but you get the idea. So over here, average rate of change equals, and then I can calculate it. I can do it. Same thing here for instantaneous rate of change. It can be positive, negative, or 0. It doesn't matter. For the average one, I don't want it to be 0. So just make it any positive or any negative is fine. Okay, now finally you get to the last page, which is the thinking, where what you're going to do is you're going to analyze in detail that row C function. So give me a domain and maybe give me a little explanation. So let's say we were looking at just this function again. So let's go, this was function t, right? So now what it might be helpful for me, for example, to copy this onto a new thing. So I'm just looking at it, right? Okay, so there's the eyebrow that was drawn. Now, what's its domain and range? Well, I can see that its domain seems to stop at 0 and also stops at 4. Now, it stops at 4 because I forced it to, right? Or rather, this student that made this picture forced it to. But even this, you can get rid of this. You can get rid of this like domain part if you want, and just tell me about the whole function without the restriction. Right? You can do that too. It doesn't make a difference to me. Just to be clear which one you're doing. Okay, so let's do the restricted version. So the domain, what I would say here, domain at 0 less than x less than 4, and x is in the double R real numbers. Okay, so x is in the real numbers. Now underneath this, I'm going to write the restriction at 0. So the restriction at 0 is because of the asymptote of log x, right? So there's an asymptote here, which is why the domain is restricted. The restriction at 4 is because I cut off the function at this value for the purpose of the drawing, right? So that's why the domain is sort of limited. Next, I'm going to go to the range. I'm going to talk about the range, right? What is the domain and the range? Now, the end behavior, for this one, it doesn't really make sense to talk about end behavior if the function is artificially restricted, right? So let's make the function again, but without the restriction. So we'll draw the full thing this time. And you can see that, like, over time, this function does not have a left side end behavior because it doesn't go there. So what I'm going to write for end behavior for this one is as x approaches 0, and remember I write from the right, from the right, as x approaches 0 from the right, f of x approaches infinity, right? INFTY, to write that in Word. INFTY. Okay, as x approaches 0, f of x approaches infinity, right? So that's what's happening on this graph as I go to the left. Now to the right, you know, logs, they take a really long time to get there, but they never stop going down, right? The log functions always go down, or up if they are positive. But this is a negative log function, right? So it always goes down. It takes a really long time. You can see it took 320,000 numbers for it to get below -2, but it will eventually go to negative infinity. It just takes a really long time. So underneath this, I'm going to write an explanation. Because of the vertical asymptote, the function doesn't have left side end behavior. Instead, it stops at the asymptote and approaches positive infinity, right? So it doesn't have. Okay, so that's that. Then under here, I'm going to write as x approaches infinity on the right side, infinity, f of x approaches, negative infinity, right? And again, an explanation, even though log decreases very slowly, it always decreases over time and will eventually go as negative as needed, right? Or something like this, right? And I give a quick explanation for the end behavior of my function doing this and so on. Okay? I'm going to talk about increasing and decreasing intervals. So you don't have to do all of them. You just pick one. My function's increasing from here to here, decreasing from here to here. Of course, GeoGebra could be very helpful in finding that. Let's go back and zoom back into this thing. Just zoom back into like the area that we were interested in before. Now let's use the limited function this time. And you can see that my range is going to be a bit of a challenge, right? Because I'm going to have to locate this point right here that is the lowest value. I might need to do some like zooming in and moving around and like looking for the lowest value to find my range, right? To find a decreasing interval, I find myself a little maximum here. Let's say this one, and then I find myself a little minimum here. And I know my function is decreasing between a and b, so I'm going to write, I'm going to write my increasing and decreasing intervals there. I'm going to list any max, mins, or vertical asymptotes. I'm going to list my positive and negative intervals. Now, for my function, it's always positive, so not going to be very complicated. I'm just going to say it's always positive because of this +3 here that shifted the graph up, and that sort of avoided all of the negative regions for the part I'm interested in. If I'm talking about the full function, then yeah, eventually I would have to look and see, like, where does it actually cross 0? And of course, in this particular function, where it crosses 0 is pretty complicated because, it actually crosses and uncrosses 0 thousands of times, right? Because it's a wave and a log at the same time. So, in a question like this, you could explain that. Or you could say, you know, for purposes of this question, I'm just going to answer it with my truncated function, the shorter function I used for the picture. And I can, if I use the shorter function, it's like it just never goes below. It never goes below 0. Right? You could say, you know, you could sort of answer both, but I would not be expecting you to like go through and find where this function hits 0 repeatedly, right? I mean, it's just not going to do that. Okay, so you give me some positive and negative intervals, and that's it, right? That's the whole thing. So I know it's a lot of work to make these pictures. So if these charts don't seem like that much work to you, you know, try to remember it's 10% of the course, right? It's like the same amount as a test. Shouldn't be taking us dozens and dozens of hours. It should take us a couple hours to make the picture and maybe an hour to do this, right? Maybe not even, right? To fill out all this information, double check that it's accurate, you know, put in as much detail and care as you can and hand it in and be done, right? I mean, it doesn't need to be more complicated than that. Okay? So, and again, like I said, if you're really strapped for time, then you know, make a simpler picture, make sure you meet the minimums of the assignment. And, you know, as long as you haven't skipped anything or, you know, written me a one-sentence paragraph, you know, you do the basics of what I asked and you're sure to be in the 80s, let's say, right? And then to go beyond the 80s, you know, that's where the like more care, more attention, more complexity, better matching, longer paragraph, and so on. That's how you can make up the difference. Okay, so I hope that you know, as much as it's possible, this is more of a project that's more you know, enjoyable and interesting than a typical test would be. Gives you a chance to stretch your knowledge in a low, non-timed, so low stress, sort of non-timed way, and you can still show a lot of what you know and earn a lot of points towards the end of the course, right? So that's if you want to choose the function art method. All right. So basically, just to summarize, you would go into GeoGebra. You can use Desmos if you're more comfortable, but my recommendation is, of course, GeoGebra. Sorry, I've got like 50 of these things. You go into GeoGebra, you go right here and you say image. So under slider, you go to image, and then it says what image do you want. Let's just go back to the example I used earlier in the course, the Neuschwanstein Castle. And I think a really good strategy for this is kind of like center it at 0, 0. Oops. How do I? Sorry, I've got this. Of course, forgot how to do this as soon as I wanted to. Okay, it's position. I'm gonna. Oh. I'm just gonna give it a corner 4. Corner 4. Okay, and now I should be able to control it a little better. Yeah. Okay. I can like warp it around and stuff. So let's say I want to like set it at, you know, the center, something like that, and then I'm going to go to its properties, and I think this is really important. You go down to its opacity and you just drop it. Right? Drop it to 20 or something so that you can see your grid very easily over the castle. Now let's say, you know, I'm looking at this little minaret up here, and I want to do, I'm thinking this kind of looks like an absolute value function, and it's located right there. So I'm going to put a point there, and then I'm going to go down. Actually, another thing you should do, I think, here is just fix your object so you can't move it. Now what I'm going to do now is I'm going to draw an absolute value function. So let's say negative absolute value x, right? It looks not bad. And then I'm going to say, let's shorten this function. So function f, comma, I want to draw it between negative 0.5 and 0.5. So I only want to draw this small part of it, right? And then what I'm going to do is I'm going to draw, like let's say lowercase e equals 0.9, 3.8. So I draw a vector that connects to the point that I want to connect it to. And then I'm going to go translate my function g using the vector e. Now this, you can see it did a pretty decent job, but I've actually drawn it too big and it's not quite steep enough. So let's go back to my function, and let's say my absolute value, I'm going to make it a bit more vertically stretched. So let's say a 1.5. Okay, that looks a lot better, right? Now I've kind of captured the edges pretty nicely. I don't want it to go this far left and right, so let's open this one and let's switch it from maybe 0.5 to 0.3. Yeah, okay, that's pretty good, right? pretty good for what I need up there. It kind of draws the top of that. Let's hide some of this stuff. Hide this, hide the original function. Maybe hide the label for that one. And I've got the first part of my castle done. Now I know this is an absolute value function. That wasn't technically on my list, but go ahead and put it on the list if you want, right? And it's a function we talked about. It's no problem. Maybe I'll add it to the list after this. Okay, and then I can go back and I can do some other stuff, right? I can maybe, make this like archway right here would be another one I could use a different function for. Or like this curve right here, I could use a log function that kind of does this like driveway or, whatever, right? Use different functions, match them, and make your picture. Okay, so that's everything to know about the function art version of this CPT. Now the other version of the CPT is the data version. So let me just shut a couple of these things down. The data one. So let's say now I'm going to go over to the other one in more detail, and this one starts rather with the communication section instead of the knowledge. So up here, I want you to write the data source. Where did it come from? Give me a very brief description of like what this thing is, what the source is. So like, I've seen people in the past do like sports analysis, right, where they, predict the number of goals that it would take to win the Premier League in the future, something like this. Let me just show you the one I'm doing, and I'll give you a website description and the scatter plot. So for me, I know I want to study the debt. I'm interested in like finances and stuff, right? So I go over here and I'm going to say U.S. national debt, and then I'm going to type time series, and a time series is like a set of points, right? So here is the Federal Reserve Bank. So obviously very important, reliable source, right? The Federal Reserve, the main national central bank of the United States, and you can see that it comes up with a graph of the debt over time, which is here. But more importantly for me, it has the time series, which I'm going to download. Okay, so I'm going to download the Excel data. I'm going to get the CSV data actually, and then we'll open it up, and you can see that the CSV data gives me once a quarter, right? So this would be January 1st, this is April 1st, July, and then October. So all the way from 1966 all the way up until 2023, right? So a lot of data. Now, I don't think your project needs 230 items of data, but let's say, it's hard to say what a number is, and the more the better. It's not that difficult to work with 200 pieces of data. I'll just show you how you would do it. So I'm going to grab all this data. Let's just do it this way. So copy A and B, and then we're going to open up GeoGebra, and I'm going to go to the spreadsheet view. Okay, so the spreadsheet view is over here, creates a little spreadsheet, and what I'm going to do here is I'm going to paste the data into the spreadsheet. Now, I kind of think that for our model, we don't really want to work with dates, we just want to work with months. So let's start with month 0, month 1, month 2, and so on. I don't want to type all these things in, so what I'm going to do here is I'm going to go A4 plus 1, which basically says take whatever was in cell A4 and add 1 to it, and then I'm going to copy that and paste it, right? And I'm just going to paste it all the way down to the bottom, right? Paste. Okay, so now you can see 228 months or 228 quarters worth of data is here, right? So this is the date, so the quarter since 1966. Okay, I guess I can't do that. Let's say quarter. I can't do that either. I'm not sure what's going on there. I guess we can just remove it. And let's do, so we're going to highlight them, highlight the data that we're interested in. And then what I'm going to do is up here, I go to where it says 1 variable analysis. I want 2 variable analysis. Okay, and I'm going to hit analyze. And then what it does is it creates for me a model, right, of all the different points. Let's close the spreadsheet because I don't need it anymore. It creates for me a scatter plot of all the values. Okay, so every one of these values is a dot, And if I copy this to graphics view, so copy to graphics view, I can see that like each individual one is a dot that represents the debt at that time, right after that many months. So you know, it's a graph. I should label it on the bottom. I'm going to label quarters since 1966. So t equals 0 is Jan 1 is Q1 1966, right? So just label that so that's clear what it means. And over here, I'm going to write debt in US dollars. And obviously, this is not how many dollars are owed. I should go back to where I said it here. It's in millions of dollars, right? So these are the millions of dollars of debt. So I'm going to go back here, debt in US dollars, and I'll just write millions, right? So that I know, the audience knows. Okay, so this is how many $1 million in debt the government of the US is. And, you know, I purposely didn't do Canada, right? Because I wanted to leave that one for you if you're interested. Anyway, once I'm here, GeoGebra has really neat ideas about how you can do different regressionary models to match the data as best as you can. So if I do a linear model, obviously a linear model here has a lot of limitations. Like, for example, in 1966, it thinks the debt was negative $400 billion or $4 trillion. And then it overestimates the debt for a long time. And then today, it's off by like 10 trillion, right? The real debt's 32 trillion, and this one thinks it's 20. So a linear model, I mean, you can pretty much look at it and say a linear model is not such a good model here, right? A log model, it can't even do, right? I mean, it's just not going to be able to do that. A polynomial model, well, the quadratic's not bad, except the quadratic like makes it seem that the debt went down for a while, when in reality that happens very, very rarely. What if we made it a cubic? Okay, well, a cubic's not bad, right? It's better. What if we made it a quartic, right? And then a quartic is actually a pretty good model, right? It's pretty slow along the beginning, and then it picks up speed, and then it kind of matches the speed today. So maybe I want to take this model. You can see like it's pretty complicated, you know. So you could simplify it a little bit, right? You could maybe take the quartic part and the y-intercept part, and maybe, you know, round off some of the numbers and so on. It's not going to make a huge difference, right? If yours is like, so like let's take an example, right? Let's take a look at this function. Let's say I changed it to 0.03 x to the 4 plus 9.3 x cubed plus 1,240 x squared, and then I'm going to go minus 36502x plus 552567, right? And oh, sorry, this should be minus. That's why I was like, why is this so far off? Yeah. So okay. So like, honestly, let me just move this over for a sec. Like, my model is not necessarily as good as theirs, but it's a fair bit simpler, and it's not bad, right? I mean, I could tinker with it a little bit if I wanted. I could take this 9.3 and make it a 9.25. It makes it a little better, you know, so on and so on. You tinker with it, right? That's kind of the point of what I want you to do. So that's one model. Let's say I want to, you know, I'm supposed to look for 2, so maybe I want my other model to be exponential, and then I'm going to copy this over. Now, this one, if you choose an exponential model, GeoGebra is going to use E by default, which is not something we learned how to do. So in that situation, what you're going to do is, let's hide the other stuff for a minute, and you're going to make the model yourself. So go ahead and take the same number that they used for the y-intercept, and then let's create ourselves, let's just change the base to base 2. Okay, so instead of e to the 2.0.0 whatever, 0.02115, okay, and then x. Oops, sorry, try that again. Times 2 to the power of 0.02115x. Oh, I see, I'm sorry. It's because it's not a function, sorry. So let's, mx, we'll make a model, is this times 2 to the power of 0.0215x. And you can see my model here is like it's too slow. So I need to horizontally compress it a bit. So how do you horizontally compress something? Make the k value bigger. So I make it with a 0, 3. Okay, that's pretty close. Maybe instead of 3, 1, I go 3, 0. Okay, pretty good, right? So I just tinker with it until I get something that works. GeoGebra will make you an exponential using e. What I would suggest, you do the same thing they did, but change it to a base of 2, and then just tinker with the k value until you get something that looks good, right? So here's my model. It fits very nicely at the beginning, very nicely in this midsection. It's under for a while, it's over for a while, but of course it's a model, it's going to do that. Okay, so that's that. Then you're done your model. Okay, once you're done your model, you go back here to the sheet. How did I choose this data set? How do I know the data is reliable? Why do I think this data should be modeled? What's interesting about it? So tell me about this topic. Right? If I'm writing about the debt, I'm gonna talk about why do I care about the debt? Why do I think the debt matters? Why is it important to model it and predict it for the future? Okay. Conclusion, at the end of the process, what did I learn? Right? What conclusion can I draw about this topic and about what I've learned in advanced functions, right? What's my opinion of this topic, right? So write about the thing. Pick something that interests you and tell me about it. Now here, you're going to do the data with the first model. So for instance, I'll go back to my quartic model, and I'm going to take a screenshot, or whatever. Again, you could send me the actual GeoGebra. It's really helpful if you can do that. I'm going to go back to my thing here, and here's my first model, right? So, and this is just delete all this extra space, and there's my first model, right? And what's the function? The function was x to the 4, plus 3x cubed, whatever. You put in the second model over here. So that's all your work for application. Both data sets, your data set with your two alternative models. Okay, and I'm marking again how close a fit is it, how much time and care has gone into creating the models. All right. Now, for knowledge, you got to do your domain and range for each one, your end behavior, and any special features. So for me, I had, for my exponential, I don't really have a lot of special features, but for my quartic, it did have some mins and maxes. It had some increasing and decreasing and so on. I would need to go through and analyze those things. Down here, I make a prediction. So let's do a couple. No reason to just do one. Let's say debt in 3 years, debt in 5 years, and then I'm going to say debt when debt when my students are 40, right? So that would be what? When you'll be as old as I am, right? So what's that? 23 years from now, or 22 years from now, maybe. And what kind of debt are you going to be looking at in that world when you're me and you're trying to raise your family and save your money and think about the future and all this stuff? What's the debt going to look like then, and what does my model say? And then I can go over here and I want to talk about how valid my model is. Now look, exponential functions grow faster and faster forever, right? So if you look at what my model says, my exponential model, right, this one, what does it say we're going to be doing in 10 years? Well, we need to stop talking about trillions and start talking about quadrillions, right? At some point, you think my model probably doesn't really work anymore. You could say 100 years from now, my model probably says that the debt is bigger than the amount of atoms in the universe, and probably that's wrong. So, of course, my model is going to have some limitations in terms of when do you think it should be cut off? Do you think this is a good model for the next 5 years, for the next year, for the next 20 years, and so on and so on? You discuss these things with me. Okay, now for thinking, you finish this up by saying which model was better and why. In my case, I would argue the exponential model is better because the debt is something that grows by 1% per year, and that's what exponential models do. So I would give an explanation of why the quartic model probably isn't going to track it very well over time, and the exponential model probably will. I talk about strengths and weaknesses of my model. So, what is good about it? Well, it matches the fact that, looked at the data this way, it's a very, very good model that matches the data well and makes sense about why it works this way. All this model is doing is saying that the debt is growing at 8% per year. That's basically what this says. So you go back and you do one of those calculations. What is 2 to the power of 0.0315? It's 2%. So 2% per quarter, the debt's going up. Now, nobody is going to be that worried or seem like they're that worried about something that's going up by 2%. It doesn't seem that big a deal, right? And yet, taken over enough time, this is a huge deal. It's absolutely staggering how big this number is and how big it will continue to get, unless something is changed. You might have seen in the news some of the arguments about the debt ceiling and so on, and this might help us understand that situation a bit better. I don't have an opinion for the record about that. I don't know enough about it, but it's a way that we can actually use our math and our understanding to understand the world better, which is the whole point of doing this, right? It's like, why are we learning these things in the first place? So you're going to talk about strengths and weaknesses, and you're going to talk about ways the model could be better. So my model could be better, for example, if I had, if I could find a combined function, let's say, that actually tracked the rising and falling. Like, it's almost like it has a bit of a sine wave to it, right? That a better model could do that. A better model might use a combination of functions, or might include more variables or whatever, right? So you look for ways that you could, maybe I could get more data going back further, and that would improve my model, or something like this, right? So you discuss with me what are ways that you think your model could be made better if you had more time and resources, right? Of course, you don't have to do them, you just have to speculate, you just have to imagine them. Okay, and that is exactly what I'm looking for the CPT. So you have two choices. You do not need to do both. You just choose the one that you think you would do a better job at, and I really look forward to seeing your work. I am imagining each of these projects is a few hours. Of course, the more you put into it, the better you will do. But even if you simply do what I've asked and meet the minimum criteria that I've laid out here, you'll be looking at a good mark, right? So take something you're interested in, show me the math you've learned, be thorough, be detailed, be accurate, and this is going to go well.